I'm Nikias from Pfinztal, and here's another video from my balcony. So I hope you're still all okay. Actually, to be honest, what I could really need now is a haircut. But hopefully, yeah, you're all okay, we're all okay here, and we're still all in our home offices. And we've got another question. And before we start, I would like to ask you to actually put your questions under the YouTube video if that's possible. So under this or any of the other ones, because it makes it a lot simpler to see, you know, what questions are around, and everyone else can also see the questions. So if you have questions, just post them beneath this video or beneath the very first video of this series. So today I would like to go into some details about polarization of transponders. So here I have a Pfinztal transponder, and as most of you probably know, it does make a great difference whether you wear this transponder in this direction or this direction. And the question is, why is this so? So to understand that, I'm pulling out my, it's a little bit windy today actually. I hope the sound is okay. So I'm pulling out my whiteboard again. So to understand the polarization issue, you have to understand a little bit about antennas. So let's assume we have our antenna here, and let's try to understand what's going on. So this antenna can be seen as a dipole antenna, and in a dipole antenna, like in your car, maybe your radio antenna or things like that, what happens is that you have a electrical field going basically from top to bottom and vice versa, and an inductive magnetic field going, let's see, around the chip. Okay, so you could think of it like this. Now, so this should be around the chip, inductive magnetic, and this is an electrical field going this way. So you can think of electrical waves, that's why we call them electromagnetic waves, always of a combination of a electric field, let's say like this, and an inductive field in the middle, and the energy is always exchanged between the two. So whether the electric field is fully there or half a wavelength later, the inductive field is fully there. Okay, or actually it's a quarter wavelength later. So the important thing here is that this field has a direction. Okay, so what I did here is actually my kids borrowed me their jumping rope and did a little video, and let's see if we can get it in here. So the first thing that I'm doing here is actually I'm pushing the jumping rope from left to right, and what you can see is that there is a wave being generated that you can see in this video, because it's going from left to right, because you're looking through a two-dimensional camera. Now if I move the jumping rope from front to back, you can hardly see the wave. You will still see a little bit because it's really difficult to move it back and forth in the perfect angle, but you get the picture. So for you with your 2D camera where you can't see depth that well, it's hardly possible to detect the wave. Now as a last thing, I rotate the rope, and that is actually what a circular polarization is. So what I'm talking about here is that in the circular polarization you are able to see the wave, and you would be able to see the wave from all sides. In a linear polarization, going back and forth or right to left, it's not possible to see the wave when you're looking at it from the wrong angle. And that's the important part. If you look at this here, the antenna of our transponder basically is the same as the camera when you look at that rope. If the wave is transmitted in the wrong angle, the transponder can't see the wave. Okay, so that's the issue with linear polarization. Now, all antennas have a polarization. Basic antennas always have a linear polarization, and almost all UHF transponders have linear polarization. That's for our residual transponder, but also for dog bones and whatever. It doesn't matter. Almost all UHF transponders have a linear polarization. And now the thing is that if you want to get the maximum power to the antenna, and you know the direction of the antenna, so you know the direction of your transponder, you're better off if you use a linear polarization, because what's limited in the regulations is the total output power of your antenna. Now, if you are looking at the rope being turned around, you see that I'm putting half of the power into a motion that is not needed for you to see it. You understand that? I have to put half of my power into a circular motion going back and forth that is not necessary for you so you can see the wave. It's exactly the same problem with circular polarized antennas. Actually, they have to put half of their power into a wave which doesn't help, which would only help if the orientation of the transponder was like this. Now, in our case, we typically have the orientation of our transponders under control because they're on the back of a bib, and we know the orientation of the bib, and therefore we can polarize the antenna and the transponder accordingly, and we do not lose half of the power. Or, you could also say it differently, we are maxing out the power that can be delivered to the chip within regulations. So that's why we have a linear polarization antenna. Now, there are some more questions. Let's see. Yep. About the antenna of the chip. Looking at the chip again, we have this linear polarization going up and down. One question that is always raised is, does it make a difference whether you see the chip from the front or like this? And the answer is no, there is no difference. If you see it like coming from here or coming from here, there is no difference at all. Actually, the reason why the antenna of the chip is wide and thin is mainly for production purposes, and second, for tuning purposes, because if you have more metal, you can make a more wideband antenna, which is better for tuning. But from an antenna perspective, it doesn't make a difference whether you come from here or from here. Think of it like a old radio car antenna, which is a very thin piece of metal, and there's also, it doesn't make a difference in which direction the wave is coming onto that antenna. This doesn't make a difference. What makes a big difference actually is when you come from this side, because now the chip has no way to actually capture the signal. Now, you may ask yourself, hey, isn't this the exact direction that our floor antennas see the chip? And the answer is yes. So for our floor antennas, what we found in lots of experiments is that there is another effect which is very crucial for spot timekeeping, and that is the dampening of the body when you're right above the antenna. So typically we don't capture the tag right above the antenna, we actually capture the tag a little bit in front of the antenna, about half a meter. And in that case, we have a wave coming this direction from down here, going onto the chip, and it's not perfect, but it's working quite nicely. The problem is, if you optimize it and do it this direction, like some of our competitors are doing, coming from below, this works quite well if the antenna is right below the chip. But actually, the antenna below the chip in an antenna mat is not the most critical part. The most critical part is actually if you want to capture the tag from a further distant away side antenna. And for a side antenna, there is no way to get the chip like this. So you want the chip to be like this. So this is the main reason why when we had to decide for one of the polarization directions, we said, hey, let's go with this direction, because then we have enough reserves if we ever want to work with side antennas, which is now especially important with our new passive track boxes coming up. So I hope this helps and gives you a little bit more understanding of polarization of our transponders. And I hope the wind wasn't too bad here today. And see you next time.